Okay, so next we're going to talk about dipole-dipole interactions. And so these are polar molecules. So they have those regions of partial positive and partial negative. So they have dipoles. They have the partial positive, partial negative charges. And so the, positive is attract to negative, opposites attract. That is, a theme I always harp on because it comes up over and over again. And so partial positive, partial negative, they're attracted to each other. And these are, unlike dispersion forces, these are constant areas of partial positive and partial negative. These are not fleeting moments. These are continually occurring. And so the more polar a molecule is, the stronger these forces are going to be. Now, what does it mean for a molecule to be more polar? Well, you can have increasingly polar bonds, so a larger difference in electronegativity in your bond. Carbon and chlorine versus carbon and fluorine, for example. Larger difference equals more polar. And you can also just have more bonds that are polar, as long as the molecule, as long as they're not canceling out in their dipoles, as long as you're still having a polar molecule. That will be the case. All right. So for example here, if we have something like HI versus HCl, well, we're looking at a hydrogen bonded to an iodine. We got a dipole like so. We got a hydrogen bonded to a chlorine. We got a dipole like so. But chlorine is further up the periodic table from iodine. It's 2 rows higher. They're in the same column, but it's 2 rows higher. So this is more electronegative. So that means there is a larger, because they're both hydrogen, so there's a larger difference in electronegativity equals more polar, which means this is the one that has the largest dipole-dipole interactions. Like if we had a container of HCl versus a container of HI, this would have more attractive forces with its neighbors. Either way, you don't want to open that container. It's going to mess you up, just so you know. So you see something labeled HCl, leave it alone. At least if it's gas, especially. If it's the acid, acids are nice, they stay in the beaker. Gases, they go everywhere. Nice yellow cloud of death. Another example would be, we're going to have some carbon chains here. Identical. This one's going to have 1 chlorine on it. This one will have 2 chlorines on it. All right. And so we have a polar bond here. And we have 2 of those polar bonds here. We'll label those dipoles. And so 2 is greater than 1. This is more polar. And so it has more dipole-dipole interaction, has stronger dipole-dipole interactions. Because we have an area that's partially positive and an area that's partially negative, but it's going to occur in 2 places. So it's twice the opportunity for dipoles to interact with neighboring dipoles. Whereas this one only has, has 1 area of partial positive and 1 area of partial negative. So we have more opportunities. So that's what we're talking about when we say more polar. You can have more of these polar bonds, or you can have a larger difference in electronegativity in your bonded atoms. Either way, you get there. So as those go up, you get stronger dipole-dipole interactions. So this is how you kind of rank within the category. All right, so next we'll talk about ion dipole and then hydrogen bonding, and we'll be, done introducing the 4 different types we're going to talk about.